All right, so first off, an apology, because on quiz day, I had office hours and was kind of wondering why no one showed up. And at quiz night, someone told me I never posted where my office was. So sorry about that. It's BA 5110. I updated the Piazza post. I put it on Discord. So I'm sorry about that. I did not mean to not tell you where my office was. Yeah, so hopefully people actually show up now. Yeah, so quiz 1 seemed to go fairly well. No? So the average so far is like 83. So the 2 short answer ones haven't been graded yet, but they'll be hopefully graded tonight, and then you can get your quiz back. So it doesn't, sorry?
Are like the grades without the long answers posted?
No. No, I can just see it. So there's 80% of it graded. I had to go through and manually grade stuff, but it's like 66 out of 80 so far. All right. So today, let us talk about semaphores. So we saw locks before, and they ensure mutual exclusion, which again means that only if you have a lock and unlock and you have a critical section, only one thread can be in the critical section at any given time. So if we have accesses to the same memory location, since there can only be one thread in there at a time, there cannot be any data races because there's only one thread, right? Data races, we need 2 concurrent accesses with at least one being a write. But this does not help you ensure ordering between threads at all. So how would we ensure ordering between threads? So let's go ahead and take a quick look at our example for today. So here is our example today. I will create 2 threads, so thread 0 and thread 1, and I will have one call print first and one call print second to run. So at this point, I have a print first and I have a print second, and say I want print first to always go before print second, and then the question is, what should I do? And to illustrate it, we can go ahead and execute it a few times. This time it worked. No bugs, and bugs, right? So given this implementation and what we already know, how would I ensure that I always see, I'm going first, this is first, and then I'm going second? Yeah.
Some sort of timer. You could sleep one of the threads.
I could sleep one of the threads, but that would be slow. Any way I could do it, that would be faster, but possibly not ideal. Yeah.
Global variable and yield. So you check if that's set the global variable to 1, and then check if it's for the second print. You check if the global variable equals to 2, and if it's not, then you yield. And only the global variable only changes to 2 once you finish printing the first one.
So if I had yield. Yeah, if I had yield and control the scheduler, I could just make always first go first and then yield, and then that's the only way. But let's assume P threads, we don't have yield or any of that stuff. So let's go down. So I created 2 threads and then I joined them, right? What would happen if I just did this? Right, so if I just do this and build or compile, then that should be fine, right? First, second. So I've just created a thread, I join it. So I only create the thread that could run print second after the first thread is dead. So that's one way I could do it. But yeah, so then it's just single threaded at that point, and also doesn't really help me if, I just want that print statement to go and then the next print statement, and then I want everything else after that to be able to be done in parallel. So this does not help that because it essentially just made our program single threaded. All right, so let's see what we can do. Oh, also, there's another solution we could do involving locks. So what about if I just did this crazy thing? So you're not allowed to unlock an already unlocked lock, but you can lock it twice. So what about if I just created a mutex, and in print first, I have unlock at the end of it with no paired lock, which looks kind of weird. And then in second, I have lock lock. So then the thinking in here is that if print first gets scheduled second, it would call mutex lock, which is currently unlocked, so this call would pass. And then it would call lock again, so the lock is locked, so I can't get it. So I'm going to be stuck here at this call. And then later, hopefully, I have thread 1 get scheduled, then it would go ahead and print off, this is first, and then unlock the lock, and now this call can go and print, this is second.
Isn't that like random?
Sorry?
Isn't that based on luck?
Yes. So
Maybe the first one, the second one to go first, and then the first one and the second.
yeah, so there is an unlucky combination here where this works actually most of the time. But remember I said if you unlock an already unlocked lock, it is undefined behavior. So what could happen is print first gets scheduled first, it prints off this is first, and it does an unlock immediately, and then that's undefined behavior. Or the other thread will just, say even unlock on an already unlocked thread did nothing, then the other thread would have a lock, and then another lock, and then the lock would, and it wouldn't progress through this, and it would just sit here forever because nothing else is ever going to call unlock. So if I go ahead and execute that, it like kind of works. So it worked, and then this is a point where the second thread actually got stuck because of the 2 lock calls, right? Any questions about that? Because that like almost kind of works, and it's kind of the idea we'll be going off today. So, again, here's our problem, and just as a note for functions, so printf is actually thread safe, and that is not always a given. So say, for instance, that our print function, instead of just a printf that happens either all at once, it kind of looks like an atomic that we saw last time, it kind of separated out in 3 different calls. So if I have 3 write calls, this is first, and the second thread I'm going second. If I go ahead and execute that, safe print, then that one kind of looks normal, except thread 2 got scheduled first, and then thread 1 got scheduled first. But if I execute it a few times, I'm going to get like kind of garbled input because it's going to just get preempted between the calls. Yeah.
Does thread safe just mean atomic?
So thread safe means no data races. So 2 threads can access it, and it'll just, one will happen before the other. You won't kind of get garbled input like this. So this is garbled input. So as an exercise for later, you could take this version of it and make it thread safe by just creating a mutex for both of them and putting lock and unlock around them. Yeah.
Why do you use write here? Because wouldn't printf in 3 separate calls still give like a similar result?
Yeah, so printf in 3 separate calls would give similar results, except that if you know the implementation of printf, it buffers calls, so it'll wait until a new line to actually do a write call.
So it won't do this? It won't do this?
Yeah, but that's like a super implementation detail thing. Yeah.
Wait, so you're saying that a write call, system call, in theory, can be like cut off in between?
Yeah.
Whereas like a printf won't.
Yeah, because internally it'll have like a mutex or something. So yeah, so it won't be cut off in between. So you won't see weird output like this.
Could a write ever like print like the first few letters and then get interrupted before it prints the second one, or no? Like it always prints.
So a write call could, generally if it's under a certain size, it just always happens. But yeah, if you tried to write out like, a megabyte or something like that, you might only get a bit of it written at a time. Because remember, the write system call returns how many bytes actually got written. So you might need to check that. But again, another huge implementation detail. So let's go ahead and see what we can do. So we can use something called a Semaphore used for signaling. Unfortunately, this is an overloaded term with Unix signals. but it's like the actual English word for signals. Like we actually want to, hey, like wave you down and make sure, like an air traffic controller or something like that. So semaphores, there's only 3 things you need to know about them. They have a value, and it's shared between threads, and optionally you can use this as to synchronize between processes as well, but for this course we'll just do it for in between threads. So you can think of the semaphore as a value, and it's just an integer that will always be 0 or greater, so it will never be negative. And then it has 2 fundamental operations on it. It has wait, which decrements the value, and post, which increments the value, and they're both atomic operations. So the only way that this is different than actually incrementing and decrementing a value is that wait does not return until the value is greater than 0. So if the current value is 0 and you call wait on it, it will just sit there and essentially block until something posts that semaphore and increases it to a 1, and then the wait would go ahead and decrement 1 from that, and then go from 1 to a 0, and then go by wait. So the fun thing with semaphores are that it just has those 3 operations. It's just the value you set, and then increment and decrement, and you can initially set the value to whatever you want. So you can also think of that initial value is if you don't post or increment it at all, it's the number of wait calls that may happen and the number of threads that could be possibly doing something in parallel. So the API is kind of similar to pthread locks. There's an init and a destroy, and then wait, and then there's a try wait, which won't block, so you can just see, hey, did I decrement the semaphore or not? And then maybe you want to do something different depending on, if you actually got it or not. And then post just increments it. So all functions return 0 on success. Generally, no one ever checks the return value except for try wait. And then in the init, it takes an address to the semaphore, and then this p shared variable, which is just 0 if you don't care if it's shared between processes, and 1 if it is. For the purposes of this course, it'll just always be 0. So it's just a semaphore, and then your initial value goes here. All right, so knowing that, let's try and make the threads always print this is first, and then this is second. So let's go to order print. So first thing I would want to do is create my semaphore. So I could do something like this. So, oops, I didn't include. Okay, so if I have these 2 functions and I want second to go first, and I have a wait call that will wait on something, where should I probably put semaphore wait? Yeah.
Is it like right on the first one when you're just declaring the thread to the first?
So in the print first? So, okay, so right here, sema wait. Okay, so when I create it, sem init, so what should my initial value be? 1, I hear 1. It can't be negative. It has to be 0 or greater.
Well, how many wait calls are there?
So far we just have 1 wait call right here. Okay, so then 1. All right, should we have a post anywhere maybe? After this one? Oops. Okay. So if we do that, let's just try it a few times, and it already didn't do what we wanted.
Need a wait in front of the second. Oh wait, so put the sem wait in front of the second print statement, and then that way, the only way you can get past that wait is to first do the print first.
Okay, so let's argue about what just happened too. So the initial value is 1, right? So say print first gets scheduled first. it makes it to the wait. The current value is 1, so it can decrement it without having to actually wait for anything. So it would just decrease it from a 1 to a 0, and then call this as first, and then post it back from a 0 to a 1, and then the other thread could go at any time, right? And then we're not going to do anything to prevent the first threads from going. So if it gets scheduled first, it just hits printf and prints it first, and then we don't have our order anymore, right? So there's one comment that said to change it to this.
But you have to change the initial value to 0 now, or else you'll just go past the wait.
Yeah, okay. So let's go ahead and change the initial value to 0 and see what it's doing now. So now if the initial value is 0, so if thread, print first gets scheduled first, it would print this as first, which is good, and then post it from a 0 to a 1, and then print second would get scheduled, and then it would hit the wait and go from a 1 to a 0, which is fine. It doesn't have to wait for anything, and then it would print I'm going second. So that's good, that's 1. Now let's see what happens if we happen to schedule print second first. So the initial value is a 0. So if we hit sem wait, the current value is 0. I can't decrement it, so I'm just going to wait. Then at some point, it's going to schedule print first, which is going to finally print this as first. And then it would post that value from a 0 to a 1. And then it would return that thread's dead. And then print second, it would come back to the second thread, which could now decrement that value from a 1 to a 0, and then it would get print I'm going second. So if we compile that, we'll get it, every time, because we just argued about both orderings of the threads. Yep.
Sorry, what is the try wait function?
Yeah, so try wait will just try to decrement it and then tell you whether or not it did. So
Wait will like.
wait blocks.
Okay.
So it blocks until it can decrement it. So if you don't want to block there and you want to just try it, you can do try wait. Yeah.
So with try wait, it will it's essentially like wait, but if it doesn't actually get passed, it will return a value for you.
Yeah, it'll tell you whether or not it decremented.
Like it will return like a number depending on whether you got through or not, right?
Yeah, yeah.
How would you know that value if you don't actually go past if you get blocked?
So it would just try to decrement it, and the return value would say whether or not it was able to decrement.
You don't actually get blocked because it's not a wait.
Yeah, yeah. So if in the normal case you'd get blocked if it was a 0. In the try wait case, if the value was a 0 and you call try wait, it's just going to be like you didn't decrement it. Sorry.
So that means it's like you can then do other stuff instead of getting yourself blocked.
Yeah, yeah.
So in this sense over here, for putting the wait and post, we have to take into account both if second got scheduled first and if first got scheduled first.
Yeah, it's exactly like, yeah, when we argued about data races, we have to kind of argue about all the interleavings. Yep.
Try wait is also atomic.
Yep. Yeah, all the semaphore ones are atomic. Yeah.
Does that mean they use like muxes within each of these functions?
No, so semaphores are its own primitive. So
But like then how are they made atomic?
So there's going to be some hardware support, or there's going to be some way to implement it. Yeah.
Would it be a data race if you had two threads on wait and the value is 0?
No, so it's guaranteed to be atomic. So as soon as, if they're both waiting on the 0, and then something posts it, only one's going to go by wait.
How do we know which one?
You don't.
Oh.
Yeah. Yeah, it's the crux of everything. We don't know.
So if it's atomic, you don't have data races?
Yeah. Yeah, so it will increment and decrement that value atomically, so it won't like lose any posts or waits,
Oh, I see.
right? But we don't know that the order. Okay, cool. So we fixed it. So this is just so the notes, so you can see that, and we can argue about that. It will always call print first, like always do the print F in print first, and then always do the print F in the second thread second. So this is us arguing that no matter what thread gets executed first, we get the same order. So what happens if we initialize the value to 0 or to 1 instead of a 0 though? Yeah, it doesn't work. So if we initialize it as a 1 instead of a 0, then if print second happens to get scheduled first, it would hit the wait and be able to get past it by changing the value from a 1 to a 0, then call printf, and then print first would go and just change that value from a 0 to a 1. And then the other way it would go is if print first got scheduled first, so it would post that value from a 1 to a 2, and then print second would decrement that from a 2 to a 1, right? All right, so here's a question. So can we use a Semaphore as a mutex? Because they kind of look similar right now. No, kind of. So wait kind of looks like lock, right? Yeah.
But wait doesn't prevent other threads from like operating, right?
So wait will prevent other threads as long as it's a 0. Right.
Oh, so what the issue with this is like you can unlock multiple times technically by adding 111.
Yeah, but okay, can we use it as a mutex if we use it properly? So
Yeah, because you only have like one instance of like the post, and then that will count as the unlock, and everyone is just trying to.
yeah, and then what would the initial value be? 1, right?
Wait, and then put a post at the end.
Yeah, so this is our counter from last time that we used a mutex for, but you know, we can use a Semaphore as a mutex. It's actually kind of like a special case of it. So if we initialize it to 1, it behaves exactly like a mutex as long as we replace lock with wait and then unlock with post. So if it's 1, it's going the first thread that makes it to the wait would decrement it from a 1 to a 0, and if any other thread tries to get by the wait, its value is 0, so it's just going to sit there and block. And then whatever thread decremented it gets to increment the counter, and then at the end it would post, so go from a 0 to a 1, and then another thread can get by wait, right? But this is actually kind of subtle, because even if we wrote this, we replaced lock with wait and unlock with post, the initial value is kind of key to see what actually happened. So what if we just made this initial value as 0? Nothing, right? So if we made this initial value as 0, then the first time a thread calls wait, it's just going to sit there and get blocked. Everything's going to get blocked because nothing is ever going to be able to call post. So they're all going to be blocked and they can't make any progress. Yeah.
Wait, so in this case we have 1, right? Like the
Yeah.
initial value. So when we encounter wait, it decrements to 0.
Yep.
And then all the subsequent threads that try to, and it waits until any of the other threads can run it, or?
Yeah, until any of the other threads can decrement it.
Yeah, so, but in this case, since all of them are like 0, right? So like none of the other threads will go past this line of execution, right?
If the value is a 1 initially,
So do the other threads have 1 in them, or?
so it's just like an atomic value. So if the initial value is 1, and then say 8 threads make it here, one of the threads, you don't know which, is going to decrement it from a 1 to a 0.
Okay.
And then, so there's going to be 7 other threads waiting here, and then one thread's going to make it by, right?
Oh,
And then execute this line, and then that one thread, whenever it's done, is going to increment it.
so then the other threads can subsequently make it and increment the counter, right?
Yeah, so as soon as that one thread that made it past is done, it's going to increment the counter back up to 1, and then one of those 7 threads is going to get it next.
Makes sense, thanks.
Yep. Yeah.
So like you can kind of use this as like just a atomic kind of add and
Yeah, if you want, you could use it as something atomic, just a atomic increment and decrement.
treat like an integer and just use that to do all your threading things.
If you can make it fit, yeah. But it has to be positive too. So it can't be negative, but you could use it as a atomic counter if you wanted. Yeah.
One more question. So if it was non-1, threads would be able to make through, right? Because it's not 0.
So if this value was a 2 instead of a 1, then 2 threads could make it by the weight, right? So we could have 2 threads executing this. So we'd still have that case where now we limited our parallelization to 2, but now we have data races too, right? Because now we have 2 concurrent accesses, and all you need is 2. Yeah.
Like the actual value of like the semaphores inside the SEMT like struct, right?
Yeah.
That I can access.
Yeah.
And can you like directly like just modify that too?
You're not supposed to.
Okay.
Yeah. Yeah.
We saw how you could like order like 2 threads, but if you wanted to do 3, would you need to do like, or like any number of threads you wanted to order, would you need to have like multiple wait statements or something like that?
Yeah, so if I added a print third here and wanted to organize it, right, how would I do that? Anyone want to hazard a guess?
Oh, you just put 2 for the, you just put 2 weights for the last one you want, and then 1 weight for the first one, for the second one, and then no weights for the first one.
Close. So what about if I create another semaphore?
You do 2, so you have 1 semaphore per order kind of?
Yeah, so I could have 1 semaphore per order. So this could be my first semaphore that posts and wait, and then I can have another one, a different one, and say, print third looks the same. We'll post here, that new semaphore, and then have a wait here. So if this always goes second and then it posts a value that's initially 0, then it's going to wait until this is done before it can execute, right?
So you kind of need the number of threads minus 1 number of semaphores to keep them ordered.
Yeah, the easiest way to do it is, if I have number of semaphores minus 1, I just kind of cascade them like that.
Is there a way to like have like a scalable way of doing this?
Well, that's just ensuring order, which kind of makes it not parallelizable. So it's only if you if you're doing some operation where the dependencies mattered, you might want to do something like this. Okay. All right, so let's come up with a solution to this. So here is our producer and consumer. So we'll assume we have a circular buffer where each slot is either empty or filled, and initially it's going to be all empty. So we have a producer that writes to the buffer. If the buffer is not full, ideally, we don't want to overwrite information. And then the consumer should just read from the buffer and then do something with the information it extracted from it, as long as it's not empty. So it shouldn't be reading just empty data that hasn't been initialized yet. So one of the ways you can implement this is just a circular buffer where all consumers share an index and then all producers share an index. And then in both cases, the value is 0 initially for both the indexes. So if they're both pointing at the first slot and we don't want the consumer to read empty data, then the producer should come first. So there's already some type of order that we want. So let's go ahead and see what the code looks like. So if we go ahead and so I'll skip some code and just show the producer and the consumer. So I essentially have a semaphore that acts as a counter. So this is just meant to like cap the number of items that we have. So you can ignore this. So in a real program, it'd probably be like an infinite loop or wait until, I know that I cleared all the data from a device or something. So in the producer, we just sleep to simulate that we're producing some data, we're doing some work, and then we will fill a slot, right? Which would just pick whatever initially would be slot 0. Whenever we have data, we'd put some data in that slot and then go to 1, to 2, to 3, to 4, and then circle back once we hit the end. And then in the consumer, it's the same, but the other way around. It will essentially just loop over and over again to try and empty a slot. And then once it has that, it should have some data. And then it can do all of that work, hopefully in parallel. So we're just getting data from a buffer and then, simulate doing some work. We should be able to do in parallel while the producer's also doing some work. Yep.
So does try might
So try wait will just return whether or not you decremented it.
So it's like 0 if you did, 1 if you didn't.
It's 0 if you didn't.
0 if you didn't.
Yeah, so this loop, so we don't have to worry about this that much, that I just set it to, like, say I want to produce 15 elements. I just set its initial value to 15 and just loop over and over again to try wait to decrement it until it doesn't decrement anymore.
But it's looping while it is equal to 0.
Yeah, so while I didn't successfully decrement it.
Okay.
Yeah. Okay, so if I go ahead and print this, or sorry, I go ahead and run it. So I have a few arguments, so I can say the number of producer threads, the number of consumer threads, then how many elements I want to produce, and the size of the buffer and how long it takes. So even if I just do one of each thread and do that, I have red text that says the conflict. So if I look at it here, the first thing it does is tries to empty slot 0, which is already empty. So that's an error. And then, it takes a while to produce some data. So now it fills slot 0, but it's already tried to be empty before. So then this is going to go on, empty slot 1, but it's already empty. And then it comes in and fills it and goes on and on and on until it finally kind of catches up. And then at some point, the filling goes faster, and then it has overwritten a slot that is already filled, so the consumer wasn't able to read it yet. So let's try and fix that. So if I want to try and fix that, first thing that's easiest to think about is what do we want to wait on? So should we wait on the producer or the consumer first? Producer? Sure.
Wait on the consumer because the producer has to do things first and then the consumer keeps it.
Yeah, okay, so we can go the other way. So we know that the consumer probably should go first. No, sorry. It should go second. Okay, so it should go second. So sem post, or no, we want to wait. And then we have to give it a name. So giving it a descriptive name, we might want to wait for a filled slot. So let's call our Semaphore filled slots. And then we can go ahead and create one, static sem. Filled slots. And then what's our initial value? 0, right? Because we want to prevent it from running immediately. So if we want to prevent our consumer from running first, the initial value probably needs to be 0, because if consumer gets scheduled first, we want the wait call to sit there and block it, right? So we all agree that that should be 0?
And then we just do post right after fill slot.
Yeah, so then if I want to keep track of the number of filled slots I have, then I should have a post after the number of filled slots, or after I fill a slot. So I increase it by 1, I filled a slot. All right, everyone good on the same page? So hopefully if we go ahead and compile that, and we run it with just one thread, hey, no problems, right? So we waited, we always filled a slot before we emptied it, and we kept track of them. So there's subtle bugs still. If I run it probably with more threads, I will see some more bugs, or not. Let's produce a lot more. So if I produce 25 things. Okay, let's be lucky. All right, usually it has a data race. 15, buffer size 10. So let's make our producer take longer. Oh, geez. Okay. Yeah, we're too good at coding. There's a case where it's not going to work, and apparently, yeah. Okay. All right, we're too good at coding. But we should protect the other way around just in case it were to happen. So the other thing we want to do is make sure we don't empty a already emptied slot, right? Or sorry, that we don't fill an already filled slot. So we only want to put data into an empty slot, right? So we can do another semaphore for empty slots. Oops. So if we do another semaphore for empty slots, and we probably need a wait here. So that way, if, for some reason that, say the buffer size is only 10, right? So say the producer produced 15 elements in a row. We want to make sure that at most it only produces 10 until the consumer actually catches up with it, right? So here we're going to wait for an empty slot.
So the initial value should be equal to the number of empty slots.
Yeah. So we need to wait here, and we need to make the initial value of empty slots equal to the size of the buffer, right? So buffer size. Okay, so now we're waiting for an empty slot, which initially there's buffer sizes. So if it all gets scheduled, I can fill up the buffer full from the producer, which is good. And then I fill a slot, and then I wait, and then I post that I filled a slot. So in the consumer, I wait for a filled slot, and then if I empty a slot, I'm missing something.
You need to post the empty slots.
Yeah, some post empty slots. All right, so I make sure that I increase that. So if it fills up the whole buffer, it waits for the consumer to empty a slot, and then it would increment it from a 0 to a 1, and then one producer could come in and fill the buffer back up. So let's compile that. Of course, no matter how many threads we get, we're going to see all the good output because we already saw the good output before, right? So even if I do, 15 threads of each, it's just going to immediately run in parallel as much as it can, right? So any questions on that? Yeah.
So this kind of method is basically allowing you to run in parallel up to 15 threads at once in parallel, right? Or whatever the buffer size is.
Yeah, up to the buffer size. So because I just had 15 threads in each, and by default the buffer size is 10.
Oh, okay.
So I essentially am wasting time creating threads that I know I don't really need to.
You have 5 extra threads that are sitting around.
Yeah, I have 5 extra threads that aren't allowed to go in parallel because I can only go in parallel up to buffer size. Yeah.
So if you had like 10 and 10 versus 1 and 1, or you made like a massive number, would it actually be quicker doing this? I don't know.
So this would be quicker as long as you can run in parallel as much as you can. And then past that, you're just going to have some overhead where you're creating threads that you don't really need to. Unless, of course, they block or something like that, in which case there's a use for them. All right, cool. All right, so here is the solution for your slides. So, first one was we ensured producers never overwrite filled slots. And we initialize the value to the buffer size. And then the other one was to ensure consumers never consume empty slots. And we set that value to initially be 0, right? Initially, we have 0 filled slots. So we used 2 semaphores, and we ensured some proper order between producers and consumers. All right, so what would happen if I initialize both of the semaphore values to 0 now? Yeah.
Nobody would produce or nobody would consume.
Yeah, so if they're both 0, no matter what got scheduled first, it would hit a sem wait at a 0, and both of them are 0, so we'd never make any progress. So we kind of deadlock ours. So it's called a deadlock. We'll see that in the next lecture. All right, so we use semaphores to ensure proper order. We saw mutual exclusion before, but now we can ensure order. So they only have 3 things. They contain an initial value. You can increment them and decrement them, and the only caveat is that the decrement will block until the value is above 0, and then you still need to prevent data races in this case. So let's go ahead quick and do a midterm question example that has to do with get context that might help for lab 2. All right, so this is from a midterm. Ashwin went over it, so I will go over it too. Hopefully it helps in lab 2. So the question says, you know that implementing thread switching is a little tricky. To simplify matters, you start by implementing a thread switching between just 2 threads, A and B, as shown below. You've already added A and B to the run queue and initialized their thread context, so they will start executing thread A and thread B functions. When they are run for the first time, your scheduler happens to run thread A first, and this is cooperative. So I will use green to say where each thread is going to execute if it was to be scheduled. So thread B got initialized to just start executing the thread B function, and it says that thread A is already executing. So thread A would start executing here. Okay, and then the question says, circle the output you expect to see. Think carefully about what is saved by the get context function. So a get context function just saves all the registers, right? So let's step through it, knowing what get context does, and explain what happens. So thread A is going to start executing. It's going to create a variable called D on the stack and initialize it to 0. So thread A will have a variable with D equal to 0. Okay, it will go into this while loop, check the value of I, that it's less than 3, so I is up here. So I is a global variable and its current value is 0. So it's going to go past the while loop and then increment it. So it would increment I from a 0 to a 1. And then it would go ahead, execute the next line, which is printf of A, and then whatever the value of I is. So this will print A1, right? Okay, so now this is where it gets tricky. So it sets D equal to 0. It's already 0, so it doesn't matter. And then it calls get context for essentially thread A. So let's put in green where it would resume if it gets, if someone calls set context on UA. So it would resume right there, right after the get context call. So let's just put that in our back pocket to know. And then it's going to check this if condition. D is equal to 0, so it's going to set D equal to 1. That is a big eraser. So it's going to set D equals to 1, and it's on the stack, right? So since it's on the stack, it will call set context, and then thread B will be the active one. So just to put a reminder as to what the value of D is for thread A, because again, it's on the stack, so it's local, we'll just put it right here and keep track of it when it resumes. So, yeah.
Is this like cooperative threading?
Yeah. Yeah, we're assuming, we're assuming that cooperative threading, so it's not going to get preempted. Yep.
So in the lab itself, they had like volatile for one of them.
Yeah.
So is that only just to make sure the compiler doesn't just put in a register and it doesn't put in the stack?
Yeah. Yes.
So if it does get put into a register, what will happen? Would it just go back to D being equal to 0?
Yeah, it depends how the compiler uses that register. So generally it does that if it's doing some optimizations, and it might reuse that register or do odd stuff to it. So volatile just forces it to stay on the stack.
So is it a good practice just to do volatile in these kind of cases where the behavior of the function isn't linear?
Yeah, if you really need it to be on the stack, you can, like in lab 2. Yeah.
Wait, I didn't know like you can put variables into a register. Like when would it do that?
So the compiler gets to decide.
Okay, so what if you try to call like address of that variable? What do you get?
So if you call address of that variable, then the compiler can't remove it.
So like it would just.
So it has to be on the stack if you take the address of it.
Okay.
So you'll see that in like some compiler course if you really like compiler courses. So if you don't take the address of something, the compiler's free to like just ignore it. Yeah.
So get context basically
Yeah, in this case, it would be the space of UA.
Yeah, so why is D equal to 1 in that case? Because it just saved its space, right? So shouldn't the next available thread run?
So, but thread A's stack still has that variable D.
Right.
And right before, we called get context, and then we changed it here.
Wait, yeah, so about that specific spot, so when we call get context, doesn't this thread like stop executing?
No, get context just saves the context, and then if you call set context of it, it'll resume. So that's why I have the green there. So if you call set context of UA, this is where it would start executing from again.
Oh, okay.
Yeah.
So you call get context, and when you call get context, D was 0. So if you set context at A, it would return from get context, and D would be reset to 0 no matter what it was set elsewhere.
No, D does not get reset to 0 because it's on the stack, right? So it doesn't reinitialize the stack because we're not calling it again. So it would have whatever value you change it to last. Right, so it's going to have a value of 1. All right, so then it called set context to thread B, which is initialized. So I'll go ahead and make that blue. So thread B is here. So it's going to allocate a D on its stack, which is private to itself, and that value is a 1. It's going to go into this while loop, check the value for I is equal to 1, then it's going to go increment it. So it go from a 1 to a 2, and then we'd hit the printf. So this time we'll see B print off 2. And then we're going to set D from 1 to 1, then do a get context for thread D, thread B. So we'll just put a little note to ourselves here that if you call set context on UA or UB, that's where it would resume. Yeah.
For where they call get context for UA, shouldn't D be 0? Because at that point, D was 0 when you called get context.
But it lives on the stack.
Oh, okay.
Yeah.
It's
So
not saving the stack at that point.
no, it only saves the registers, right? Context just saves the register. So it saved the stack pointer,
Right, okay.
but we changed the value,
Makes sense.
right? So this is where the question gets tricky, is that get context and save context just restore registers, right? So if it's on the stack, it's just going to live there unless you exit the stack or do something weird. All right, so thread B is going to come here. If D is equal to 1, which it is, it's going to change D from 0 to a 1, and it's going to be the same thing we saw before. So D is now going to be a 0, and then it's going to set context UA, which would resume back there. So let's go ahead and just write down thread B. So when it resumes, D is equal to 0 because that was the last value it set. It was on its stack. All right, so thread A is now the active thread again. So thread A, we have D equal to 1. And then let's point. So if we have that, we resume at this point. Yeah.
For these types of questions, we're assuming that all these variables are on the stack. There's not some weird thing that they get saved to registers.
Yeah. You just assume that the compiler doesn't do anything weird. So now D is 1, so this if statement wouldn't go through. It would come back up, check while I is less than 3, which it's 2, so it's all good. Then it's going to increment I. So we're going to go from 2 to a 3, and then hit the printf again. So we'll see a 3. Then it's going to set D equals to 0. And then call get context for thread A. So it would go ahead and resume there if it were to get scheduled again, or if you called get set context on it. So D0, go in here, set D equals to 1 on its stack, set context to UB. So D, again, on its stack. The last thing we did is make it a, 1. D equals 1. So now thread B is going to execute again. It's not going to go into this if statement, so I'll just keep it green for now, but this is the current active thread that I'm kind of moving around. So it would go here and then exit this, go up to the while loop while I is less than 3. I is currently 3, so it would fall back out of the while loop and exit, and then our program's done. So we get A1, B2, A3, which corresponds to an answer, F. Yay. Yeah.
So in this, for cooperative threads, if one of them exits, they all exit?
In this case, it just kind of gets stuck. But yeah, they should all exit. All right, so that's time. So just remember, I'm pulling for you. We're all in this together.